Section 2.3, more on solving linear equations. Here at the beginning of the section, on page 117, she has a blue box that outlines a general attack for solving linear equations in one variable. Blue box, middle of the page, page 117. Step 1, simplify both sides. Step 2, isolate the variable on one side. And step 3, get the variable by itself. Now I'm paraphrasing what she has, but those are our basic 3 steps. Simplify both sides, get the variable on one side, get the variable by itself. And of course, she has step 4 to check, that is, plug your answer back into the original equation to make sure it results in a true statement. The rest of the section is primarily examples, and so we'll turn to the homework set and start working some problems. There's really nothing new in this section. We have all the rules that we need from the previous 2 sections. We're just going to put them together now. Let's start with number 10. Simplify both sides. Well, both sides are simplified. There are no grouping symbols. There are no like terms to combine. Both sides are already simplified. All right. Get the variable on one side. Well, the variable exists only on the left-hand side. So we're ready to start getting the variable by itself. What prevents the x from being by itself? It's being multiplied by 4, and then that is having a 3 added to it. So what do we get rid of first? Well, think about it this way. We're trying to undo what has been done to the variable to get it once again by itself. If we're trying to undo what's been done, we're trying to dig it out from under this 4 and this 3, then we need to approach the order of operations backwards. That is, we will deal with the plus 3 before we tear apart this 4x. Another way to look at it, the addition of 3 is less bound to the x compared to a multiplication of 4, because multiplication outranks addition in the order of operations. So we'll start by getting rid of this 3. It's being added to the 4x. We want to subtract it. What I do to one side, I must do to both sides. On the left-hand side, the 3 subtract out to leave just 4x. On the right, 27 minus 3 leaves 24. Finally, to get x by itself, the x is being multiplied by 4, so we'll divide both sides by 4. The 4's cancel on the left to leave x, which is what we're after. On the right, 24 divided by 4 is 6. This one's not tough to check. Plug 6 back in. I think we can do this mentally. 4 times 6 is 24, plus 3 is 27. That checks. Let's look at number 20. Now, I want to do number 20 2 different ways for you. Once we get it copied up here, we're going to look to see if we need to simplify. And in this problem, both sides are already simplified. So we're ready now to collect our variable on one side. Now, in section 2.1, I said let's collect that variable on the side where there are more to start with. So we'll have a positive coefficient. In section 2.2, we figured out that's really not that big of a deal. And so the 2 ways I want to work this for you is, one way, bring the variable to the left, and then go back and work it a second way, taking the variable to the right, seeing that we get the same answer both times. You should at least get to see this once in an algebra class, right? Let's do what we were doing in section 2.1. That is, let's take our variables to the side where there are more to begin with, where my variable will have a positive coefficient. Negative 16 is smaller than negative 8, so let's take our w's to the right. To take our w's to the right, we will destroy them on the left, adding 16w to both sides. On the left, the 16w subtract out to leave just that minus 3. And on the right-hand side, we have our 13. And now, that's 16 minus 8. 16w minus 8w is plus 8w. We've isolated our variable on one side. Now we want to get the variable by itself. What prevents that? It's being multiplied by 8 and having 13 added to it. We'll get rid of the 13 first. Subtract 13 from both sides. On the left, that gives me minus 16. On the right, the 13 subtract out to leave only the 8w. And finally, divide both sides by 8 to find that w equals negative 16 over 8, negative 2. Let's go back and rework this time taking my variable to the left-hand side. Again, both sides are already simplified. We're ready to move our variable. We've decided this time to collect w's on the left. That means we want to destroy them on the right. We'll add 8w to both sides. On the left, this gives me a negative 8w minus that 3. On the right, the 8w subtract out to leave only 13. And now, same approach. We want to get w by itself. We'll get rid of the numeric term first, and then finish off by removing the coefficient. Add 3 to both sides. That leaves me negative 8w equals 16. And this time we're dividing both sides by negative 8. And no surprise, we get the same answer. Because at no point did we break the rules of algebra. So long as we don't break the rules of algebra, we can do it a little bit different way from each other and still get that same result. Number 26. In number 26, we do have some simplifying to do on each side. I'm sorry, I said that wrong. The right-hand side is already simplified. So we don't have any simplifying to do on the right, but the left does need some work. So looking at just the left-hand side, let's simplify this, which means what? Remove any grouping symbols, combine like terms, perform any operation that can be performed. We'll start by distributing the 5. That'll drop those parentheses. I'll get 10m plus 15. In my next step, we'll combine like terms. 10m minus 4m leaves 6m. And plus that 15. The right-hand side is just waiting patiently for its turn. Both sides are now simplified. We're ready to get the variable on one side. Let's bring our m's to the left. That is, destroy them on the right, subtracting 2m from both sides. On the left, that leaves me 4m plus this 15. On the right, the m subtract out to leave that 25. We've got the m on one side. Let's get it by itself. Get rid of this 15. Subtract 15 from both sides. On the left, all we're left with is 4m. On the right, 25 minus 15 is 10. To get m finally by itself, divide both sides by 4. On the left-hand side, the 4's cancel to leave just m, and on the right, we have 10 divided by 4. If it divides evenly, we do it. If it doesn't, we at least check for lowest terms. So I will ask you, what is 10 divided by 4? All we can do is reduce it. 10 divided by 4 is 5 halves. To this point in this section, really nothing new. We're using our addition property of equality. We're using our multiplication property of equality. But let's take a look at this next equation, which I'm just going to make up. I want you to consider the equation x plus 1 equals x plus 2. And I want to think about this as a first grader, trying to fill in that empty box with something that will make the statement true. And I just want you to think for a minute. What could I put in for x that would make this statement true? What number can you add 1 to and get the same result as if you added 2? Well, that doesn't make any sense. Would you agree that the right-hand side is always going to be 1 bigger than the left? No matter what you plug in for x, the left-hand side and the right-hand side cannot be made to match. Now let's consider this algebraically. If we follow the mechanics of solving an equation, I would simplify both sides. That's done. I would collect my variable on one side. Let's say we're going to collect the x's on the left. That means we're going to destroy the x's on the right by subtracting x from both sides. Now on the right-hand side, just as I expected, the x's subtract out to leave just that 2. But much to my surprise, as I check on the left, the x's subtract out here as well to leave just that 1. We have a statement that says 1 equals 2. This is a false statement. What do we know about the addition and multiplication properties of equality? If we follow them, then we write a series of equivalent equations. That is, every equation has the same solution. A solution is a value I can plug back in for x that makes the original statement true. Here at the bottom, we have an inherently false statement, regardless of the value of x. There are no x's left in my equation, and this statement is false. What that means is that being equivalent to the top equation, that top equation must also be false, no matter what you plug in for x. A solution is a value I can plug in that makes the original statement true. We've just discovered, algebraically, there is no such number. And so this equation has no solution. Now, when you look this up in the back, remember, she talks in terms of solution sets. In other words, a moment ago, when we had our m equals 5 halves, she would have written the solution set, the set containing 5 halves. When there's no solution, what goes in the braces? Well, nothing. And this is a symbol for the empty set. It is a set that contains nothing. It's like having a dresser drawer that's empty. This also means empty set. And this is the symbol that she will use in this textbook to indicate an empty solution set. In other words, that there is no solution. I will take any of these on a quiz or a test. When you look it up in the back, you're going to see this Ghostbuster looking symbol. An equation with no solution. All right. Let's look at another kind of equation that we haven't seen before. Consider the instructions simply say solve, and that's all they say. Like for any of these equations. And so our approach, simplify both sides. The left-hand side needs to be simplified. We will distribute this to right-hand side is already simplified. We'll combine like terms. 2z plus z totals 3z. And I look and I notice that both sides are exactly the same. In other words, anything I plug in for z at this moment would make this bottom equation true, which implies what? That any number I plug in for z in the original equation would make the original equation true. Any real number. As soon as I get to a true statement, I can stop. This is also called a reflexive statement. Something equals itself. It's looking at its own reflection. A reflexive statement. As soon as I get to something equals itself, I can stop and I can say, that's true. Now, to make a claim that you have a false statement, you have to remove the variables. You have to remove the variables before you claim it's false and no solution. But once you get to something equals itself, you can claim, well, this is true for all real numbers. And so the solution set is all real numbers. When you turn to the back, this is how she'll write the answer. I believe it's enclosed in curly braces. But I will also accept, because you remember from chapter 1, we did introduce this notation for the set of all real numbers. So if you want to give me a double-barred R, I'll take that on a quiz or a test. And of course, you'll see me use that as we work problems here at the board. Now, I want you to be very careful with these situations of no solution or all real numbers. Make sure that you are following the rules of algebra. Think about this equation. It looks like our equation where we had no solution for x. X plus 1 equals x plus 2. Well, that can't be right. And we saw algebraically there was no solution. Well, 3 times the number. How could that be equal to 4 times the number? That can't be right. Or can it? Let's solve this. How about I divide both sides by y? The y's will cancel to leave 3 equals 4, which is an inherently false statement, and so this equation has no solution. And I will count that completely wrong. Let's be reminded that in section 2.2, our multiplication property of equality and the multiplication property extended to cover division both said I cannot multiply or divide by 0. And the warning here on page 113 at the top, our brown box, what did she say? She said, do not divide each side by a variable because the variable might be equal to 0. And that's exactly what we did. Think about this original equation. 3 times 0 would equal 4 times 0, wouldn't it? That would check. So y is 0. We divided both sides by 0 without knowing it. That's the reason we don't multiply or divide both sides of an equation by a variable expression. At least for now. In chapter 6, we're going to see some things and we're going to figure out how to work our way around that. But for now, how would I work this problem? Think about those steps from the blue box at the beginning of this section. Simplify both sides. Done. Get the variable on one side. Well, let's collect our variable on the right, just because that's what I feel like doing. If I'm going to collect the y's on the right, I need to destroy the y's on the left. Subtract. So we're using the addition property of equality to do this, as it extends to subtraction. Subtract 3y from both sides. Now, on the left-hand side, 3y minus 3y leaves 0. 4y minus 3y leaves 1y. Of course, we write just y. And y equals 0, which we know now to be the solution, because we can plug that back in and it makes the original statement true. Make sure you're following those steps. You can have an equation that looks like, hey, there's something up here. But when you follow those steps, it'll clear it up for you. This is why I said, before claiming that you have a false statement, you have to get to a point where the variable is removed. Remember our first no solution equation, well, the only one we've worked so far, we got down to 1 equals 2, and the x was gone. That's when I said, now we have a false statement. When it comes to a true statement, as long as something equals itself, with or without the variable. And this type of equation is neither of those. This has a single solution. If you look in your text, here on page 122 at the top. On page 122 at the top, we're told that these are the 3 types of equations. You have in your final line, x equals a number, one solution. That's what's currently on the board. Y equals 0. That's called a conditional statement. It is true on the condition that, in this case, that y is 0. Then she talks about an identity. That is a true statement. She says with no variable. And when it comes to linear equations, I'm going to say we don't have to worry about that. Remember, we got down to what? 3z plus 12 equals 3z plus 12. It's okay to go ahead, because this is linear, and say we have a reflexive statement, this is inherently true. If it makes you feel better, then just always eliminate the variable before you say true or false. We could have subtracted 3z from both sides, gotten down to 12 equals 12, and that is definitely true, regardless of the value of the variable. Now say that your solution is all real numbers. But here in the second line of the table, it says if you get down to a true statement, then you have infinitely many solutions, and the solution set is the set of all real numbers. And finally, when we have no solution, it's called a contradiction. That's when it boils down to a false statement with no variable. Now here I have to insist, I agree with her on this, with no variable. That's the only time you can claim a false statement, is when the variable is gone. If you get down to a false statement, there are no solutions, and the solution set is the empty set. Let's keep going in our homework. Let's grab number 30. The instructions say solve. So we're going to start by simplifying both sides. The left-hand side needs to be simplified. The right-hand side is ready to go and just waiting. On the left-hand side, I will distribute this, this negative 4. Watch your signs. That'll give me minus 4x and minus 4. Combine like terms. 6x minus 4x is 2x. You see something's up because we've got a 2x on each side. Is this a true statement? No, but I don't want you to claim that it's false until that variable has been removed, because funny things can happen. Let's try to collect our x's on the left, destroying them on the right. Subtract 2x from both sides. And that leaves me negative 4 equals positive 4. The variable's gone. I'm ready to say that is a false statement. So there is no solution. And you are welcome to write out the words, no solution, and put a box around it. On a quiz or a test, I will typically use her notation from the book and show this empty set. I waited to claim it was false until the variable was gone. That we have to insist on. Don't put a box around the word false. The instructions say solve. What's the solution to this equation? Is the solution the word false? Plug the word false back in for x and see if it... No, that's ridiculous. Think. Don't put a box around negative 4 equals 4. That's not a solution. What is the solution? You can either write no solution or an empty set symbol. But don't box the false. Don't box the false statement. Those aren't solutions. Those are steps to get to my answer. Number 36. In number 36, both sides need to be simplified. Distribute this 3, distribute this 2. On the left-hand side, distributing the 3, we get 18 and minus 12x. On the right, we have minus 12x and a plus 18. Do you see already that the two sides are exactly the same commutative property of addition? The negative 12x, the positive 18, those two sides are the same. I would be fine if you stopped right here and said, I have a true statement. You can keep going. If you don't want to have to worry about remembering when to get rid of the variable and when it's okay not to, just always get rid of the variable if it comes to one of these. Add 12x to both sides. That leaves me 18 equals 18. Clearly an inherently true statement regardless of the value of the variable. And if this is true regardless, then the original is true regardless, meaning I can plug in any real number for x and the original will be true. So my solution set here, all real numbers. And this is how I would phrase it, multiple choice on a quiz or a test, because that's the way our book does it. Like I said, you are welcome to simply write all real numbers using our double-barred R. All right. Let's crank things up a little. Let me give you an equation. We're just going to work through it. This is not from the homework set. This is just one that I'm making up. Fractions. Solve. Let's solve this equation the way we have any other equation to this point. Simplify both sides. Both sides are simplified. Get your variable on one side. The x's exist only on the left. All right, now get your variable by itself. Just as we would do in any equation, we're going to remove the numeric term first and then come back for that coefficient. Subtract 3/4 from both sides. On the left-hand side, the 3/4 subtract out to leave me 1/2 x. On the right-hand side, I don't know what I have yet. I need a common denominator to be able to add or subtract fractions. Least common is 12. So I need a factor of 2 top and bottom. I need a factor of 3 here, top and bottom. This is now 10/12 and minus 9/12. So the right-hand side boils down to 1/12. We've discovered that the easiest way to remove a fraction coefficient from a variable, we talked about this in 2.2, if the coefficient is a fraction, the slickest thing to do is multiply both sides by the reciprocal of that fraction. The reciprocal of 1/2 is 2. 2 over 1 if you want to see the over 1. Multiply both sides by 2. On the left, the 2's cancel to leave 1x, or simply x. On the right-hand side, you could multiply the tops, multiply the bottoms, and reduce. You'd get 2/12, which is 1/6, or you can cross-cancel. 2 goes into 12 6 times, which also gives you 1/6. So 1/6 is my solution. We could plug it back in to verify that it makes the original statement true. But here's what I want to do right now. I want to go back to this original equation, and I want to think. I showed you one place in section 2.2 where I could get rid of the decimals from the equation. There was a single decimal place in the equation, and so I multiplied both sides by 10, and I wiped out the decimals. I can do the same kind of thing with these fractions. There's nothing wrong with what we've done, but this may not be the best way to do the problem. I look at all the fractions involved. Find their common denominator. Least common denominator for 2, 4, and 6 is 12. Multiply both sides by 12. This 12 is guaranteed because it's a common denominator with all these. It will cross-cancel completely with these denominators. In other words, when I'm done carrying out this multiplication, there will be no denominators. There will be no fractions. So here we go. Distribute the 12 to each of the two terms here on the left-hand side. 12 times 1/2. Half of 12 is 6. Plus 12 times 3/4. You ready to cross-cancel on the fly with me? 12 divided by 4 is 3. Times 3 is 9. Remember? That's a 12 over 1 times a 3 over 4. 4 goes into 12 3 times. So all I'm saying, 12 divided by 4 is 3. Times that 3 is 9. 9 over 1, we just write 9. You got it on this side? Cross cancel on the fly ahead of me. "12 divided by 6 is 2. Times 5 is 10. I like this equation a lot better than the original. I mean, we've got to make friends with fractions, absolutely. But if I can work the problem without fractions, all the better. And by multiplying both sides by the least common denominator, which I have the multiplication property of equality allowing me to do that. The equation is still balanced, it's still equivalent, should have the same solution. Using that least common denominator, I've removed the fractions from this equation. Let's finish this one off. Subtract 9 from both sides. Divide both sides by 6. And it's no surprise, because I never broke the rules of algebra, I have exactly the same solution I did a moment ago. Like I said, in this section, it is an option. You can work with the fractions in place, but I strongly encourage you to learn how to clear these fractions from an equation. In Chapter 6, it will no longer be an option. You will not have the option of working with the fractions in place. Because of the nature of those equations, you will have to clear the fractions from the equation. All right, let's try one from the book. Let me also give you a warning. This works for an equation because you have two sides. You can clear fractions from an equation. You cannot clear fractions from an expression. Section 1.7. Okay? Let's take a moment before we work another equation. If I say simplify, let's say, I don't know, 7/5 x plus 2 minus 3/5 x. You cannot clear those fractions because there aren't two sides. There's not a left and a right. There's no keeping it balanced. If you multiply through by 5, your answer is going to be 5 times bigger than it should be. In this problem, you have to simply go with the fractions. And I made this one easy for us. If we didn't already have a common denominator, we'd need to get one so we could add those coefficients. 7/5 x minus 3/5 x is 4/5 x. And plus that 2. You cannot clear fractions from an expression. You can, however, clear fractions from an equation. So let's do another one of these equations. Let's grab number 42. We have fractions in our equation. We could work with the fractions in place. We saw that in that first equation I did and did not clear the fractions from it. But it's generally slicker, and like I said, later down the road, we will have no choice. It's generally better to clear these fractions. Multiply both sides. Multiply both sides. When I say both sides, those big parentheses go up. Multiply both sides by the least common denominator of all the little fractions. My fractions have denominators of 5 and 3. Least common is 15. Multiply both sides by 15. This should clear the fractions from the equation. And now watch this. On the left-hand side, I have to distribute that 15 to each of these three terms. Even though this term is not a fraction, this third term is not a fraction, you still have to hit it with the 15 because you're multiplying both sides. If you don't hit every term with that 15, you've thrown the equation out of balance. You are no longer solving the same equation. Distribute that 15 to each of the three terms here on the left, multiply it out by that one term on the right. You ready to cross cancel on the fly? Here we go. 15 times 1/5. 15 divided by 5 is 3. Times 1 is 3. 3x. And minus 15 times 2/3. 15 divided by 3 is 5. Times 2 is 10. No mystery here. 15 times minus 2 is minus 30. On the other side, 15 times 2/5, this term will be negative. 15 times 2/5, 15 divided by 5 is 3, times 2 is 6. If you need to see that cross canceling, you can always go off to the side and do some scratch work. We now have an equivalent equation with no fractions. So let's keep going. Simplify both sides. Here, the left-hand side, I can combine like terms. I'm going to take my x's to the right. I'm going to take my x's to the right because there are no numeric terms on the right-hand side, only x terms. It's going to save me a step compared to taking it to the left. I'll add 7x to both sides. That gives me negative 30 equals, x. Not only did we get x to one side, but we got x by itself. Number 44. And I want to pay very close attention to number 44. We've talked about terms, and we've got to be able to count terms to make this work. Now, in your book, she has another way of doing this problem. I'm not a fan of that particular method. You might be. In your textbook, you might consider the method that she shows in example 9. She starts by distributing these fractions and dropping the parentheses. So look at example 9 for a different way to go about doing what we're going to do here. She starts by distributing the fractions. Nothing wrong with that. She ends up with 4 separate terms on the left-hand side in the next step. And then she clears the fractions. Here's what I would rather do. There are no fractions trapped under parentheses. So I don't see the need to distribute those fractions at this time. I'm ready to clear these fractions. Let's clear the fractions. Multiply both sides. Now, before I put up these parentheses, I want you to tell me, this expression on the left-hand side, how many terms do you see? Terms are separated by pluses and minuses, unless those pluses and minuses are buried in parentheses. How many terms do you see? There are 2 terms. 2 terms here on the left-hand side. Remember, signs belong to their terms. That's why I drew the boundary there. These are the 2 terms of the left-hand side, meaning when I go to distribute, I'll distribute to these 2 terms. I'll draw 2 rainbows, in other words, as I go to distribute. So keep in mind, we have those 2 terms and only 2 terms on the left-hand side. Multiply both sides by the least common denominator of the fractions involved. We have fourths, we have sixths. Least common is 12. We've got to hit the right-hand side with the 12, whether these fractions or not. We've got to keep things balanced, right? And on the left-hand side, we will distribute this 12 to each of the what? Each of the 2 terms that we see. As we distribute this 12 to this first term, the 12 is going to multiply times the 1/4, and we'll get 3. A quarter of 12 is 3. The pink 12 will never make its way inside the black parentheses. 12 times a quarter times that. 12 times a quarter is 3. And 3 times that is what we're left with. The 12 does not make its way into the black parentheses. It is completely absorbed by that 1/4. 12 times a quarter is 3, times the rest we'll deal with in a minute. And plus, distributing to this second term on the original left-hand side. 12 times 1/6 times the rest. 12 times 1/6 is 2. That's just 12 divided by 6. 12 times 1/6 is 2 times the rest. That 12 does not make its way down into those black parentheses. On the right-hand side, 3 times 12 is 36. Moving on. We have removed the fractions from our equation, and we'll solve it the way we have been. Simplify both sides. Distribute that 3, distribute that 2. Gives me 9x minus 3 plus 2x plus 6 and equals 36. Combine like terms. 9x plus 2x is 11x. Minus 3 plus 6, signs belong to their terms. Minus 3 plus 6 is plus 3. Subtract 3 from both sides. 11x equals 33. And divide both sides by 11 to find that x equals 3. Make friends with fractions. Pay attention when you're clearing fractions from equations. Make sure you know how to count how many terms you see so you know to how many terms you are distributing. I'm going to leave it at that. I'll let you get on with the homework. I do want you to think about the future sections. We're about to get started on word problems. I need you to get really good at solving equations, because in word problems, solving equations is just one part of a bigger problem. So get this section down pat. We really need to before we begin the next section.